Okay, so for today, so we want two topics for today. So the first topic is, so what do we do on Monday? So on Monday we just did the absolute simplest possible thing, which is just do a 90-degree RF pulse on a even grid. So that you have so you define the idea of TR, time of repetition. So you just repeat a 90-degree pulse at a regular interval. And we worked through the solution to the block equation. So we weren't using the block equation. The block equation was the differential equation, but we're using the solution to the block equations, to the T1 and T2 part of the block equations. So basically, when you actually do more complicated pulse sequences, what happens is you have to take the solution to the block equation and then plug that back into another copy of the solution of the block equation, sometimes 5 or 10 times to figure out when you're down the line, like a couple pulses down the line, what the signal actually is. So that's what we're going to do today, and we'll start with just this concept of inversion recovery and still no echo, and then we'll go through in detail the equations for SpinEcho, so you can see how the different settings of the TR, which is the repetition time, and TE, which is the echo time, affect the contrast in the image. So this is all about contrast, meaning how do we emphasize the brightness difference between tissue types that have different T1 and T2. So different T1 and or different T2. So inversion recovery is one way of emphasizing the contrast difference. And so inversion recovery is a very, very straightforward pulse sequence. And we'll just look at simple inversion recovery with no echo. So what is inversion recovery? Inversion recovery, if you do a 180, that's an inversion. So what does that mean? Well, that means if you have a, you start off with your initial magnetization, and if you do a 180 pulse, you basically you make the longitudinal magnetization negative. So that's kind of a little counterintuitive, like how could you make it negative? But what you can think of is you're just injecting energy into the system, and so the system has sort of arrived at a low energy state with lined up with some percentage of the protons lined up with the B0 field, and so you inject this RF energy into the system. If you inject enough, you can actually invert the magnetization and make the local magnetization, the M vector, reverse direction from the B0. So the B0 vector is that direction, and this is the M vector. And so it's possible to make that negative. So that's called an inversion. And inversion recovery just means if you now turn off the RF pulse, so this is the RF. So if you turn off the RF pulse, then what's going to happen is the magnetization will slowly go through zero and then slowly regrow. And you can use the block equation solution to figure that out. Now, if you think about that, you're not going to get any signal because the signal only comes from the transverse magnetization. So, this is the longitudinal magnetization that way, which is the Z direction, and the transverse component of it is this direction. So there's no transverse at all. So if you do a perfect if you do a perfect 180, and so you nail it so that you don't end up sort of overshooting or undershooting RF pulse, then you won't get any signal. So so during the whole inversion recovery, there's no signal because there's no transverse component of it. So the vector just sort of goes through 0 and then goes back up to the MZ0. So this is, normally this would be the MZ0 that you would start with. Just off the edge, okay. So inversion recovery is if you want to do anything with inversion recovery, you at some point you have to actually do an RF pulse that's going to generate some transverse magnetization that you can record. And so for that, we need to do, say, like a 90-degree pulse. Let me make it out a little further so we have some time for the inversion recovery. Inversion recovery takes quite a long time because T1 regrowth, takes like a second or two. And so if you do an inversion, it's going to take even longer. So this, this time could be something like, a second in here. So here's the 90-degree pulse, and so that time is labeled the time of inversion, and so the problem is that looks a lot like T1. So I'll try to be pretty clear about distinguishing T1 and Ti. So Ti is for time inversion. And then after some later amount of time, we'll do another 180, and eventually another 90. So this whole time here, between the 180s is the TR. So at the exact same amount of time later, we would have another 90 out here, etc. So that's the TR, and there's various different notations here. This one, I always make a joke about this. Siemens managed to patent TD. They patented an acronym to try to prevent GE from not using it. So that's the time delay. So that's the time between the 90 and the next time you do the 180. So this is the simplest. So this one would generate a signal, not particularly an echo. So we don't have a spin echo or a gradient echo, but it would generate a signal because once you do the 90 here, there's going to be some transverse magnetization. So what I'm going to plot is the longitudinal magnetization. So not the transverse, not the recordable. So if we look at what's going on and plotting the magnetization longitudinal, and here's 0. So we're starting off, we're assuming that nothing happened before this. So you just went in the magnet and stayed in there for a while. And so the magnetization will be at MZ0. So that's the equilibrium magnetization that you get if you just go in the magnet. So then what happens is the very first thing we do is a 180. And so what 180 is going to do is make the magnetization go all the way down to negative MZ0. So it will reverse the sign of the magnetization. That's the inversion. And then inversion recovery will start to happen. So at this point, we're going to do a 90. So let's let inversion recovery happen for a while and say it gets a little bit over, it recovers to a little bit over zero. So there's a little bit of longitudinal, positive longitudinal. Then we do a 90, and the 90 will essentially knock out, if we do a perfect 90, it's going to completely get rid of the longitudinal, so we only have transverse, but we're only plotting the longitudinal, so you can't see it on this graph. And then what will happen is we will recover until we get up to this point. So here's what we would recover to if we waited a long time, but we're not waiting that long. We're only waiting, like, say, a second or something like that. And so what's going to happen is this will start to recover, but it won't quite make it all the way up. So it's going to make it up to a point that's less than if we had just let it run for 4 seconds, because this time delay is going to be like 1 or 2 seconds. So at that point, we do another 180. And so now we're going to go do a 180, and it's going to go to a point that is less than negative mz0. So here's going down to negative 180. And then what's going to happen is we're going to recover for a while, but we're starting from a higher point. And so we're going to recover to a higher point here than we did last time, because we started from a higher point right here. And then we'll do another 90, and then some recovery will occur. And so what we want to do is try to figure out when we get to the steady state. So if we assume we have a perfect 90 and perfect 180, like we said can never occur, but let's just assume that that's what occurs, then basically we reach the steady state here. So steady state is reached just before we do that. So steady state here. So we just have to do one 180 and a 90 until we get into the steady state, and the signal will be the same each time. So what we want to do today is just go over the equations for using the block equation solutions and replugging them into themselves, just to see how this works, because this is basically what all the problems are. So I went back and looked at my video from last year, and I realized I was the final equation I got for inversion recovery was correct, but the one right before it, I left out one of the terms, because I was sort of looking at my lecture and trying to go through, and I said, like, that doesn't follow. How does that work? So I'll correct it this time. So let's start with our equations here. So the very first thing is we'll start with 1. So basically 1 is we'll put 1. I'll put these things on the diagram. So basically 1 is immediately after we did the inversion. So this is 1 right here. So that is just mz0 equals minus mz0. Okay, so that's the effect of our inversion. We just did a negative to our equilibrium number. So then this is going to start to recover, and so we have to use the equation for the block equation solution for T1, which has 2 parts. There's the 1 minus e to the minus t over T1, and then there's the whatever starting magnetization you had times e to the minus. That's the mz0 plus. Whatever starting magnetization you had affects it. So there's a recovery that just happens no matter what, and then you also have to sort of add in how much your starting was different from 0. So basically, what is that going to be? So if you look at the block equation solution, what you'll get is mz now no longer mz0. So the z magnetization is just going to be equal to that first term in the block equation, but you're going to also have the second term. So the first term is 1 minus e to the minus t over t1. The second term is your starting magnetization. And your starting magnetization happens to be the same thing as mz0. So starting magnetization that you plug into that second term of the block equation. And so if you just do the algebra there, the number you get is 1 minus 2 times e to the minus ti. So now we're substituting in for t. This is our substituting in for t in the block equation solution, that ti, divided by t1. So here's that's supposedly different looking. I'll draw it big enough. Hopefully you can see it. Okay, so the two part. So this part, because second term in block T1 solution. Okay, so now that tells us that's number 2. So I'll draw it in red here so you can see it. So that was 1, and then so that was what happened. That's where we got to here. So that's 2. So now what happens is we do another 90. So what's that going to do? That's just going to get rid of all the transverse, all the longitudinal magnetization. And so pretty much we can just ignore this. Okay, so ignore. So after calculating that, we don't care about it because we're starting from 0 because we did a 90. Now we might not use a 90, and then you'd have to do something more complicated, but since we used a 90, there's no longitudinal at all, so we're just starting from 0, so it doesn't matter what it got to because we're just resetting to 0. So now we have to calculate this amount, and so what is this amount of time? So this amount of time is basically TR. It's TD, TD, but that equals TR, minus TI. So now we just need to just start from scratch with the block equation T1 solution and just write our mz is now going to equal there's only the first term because the second term, the mz 0 plus that you're starting with is 0. So basically it's just 1 minus e to the minus tr minus ti over t1. Sorry. So there's 3 different things there. So there's tr minus ti inversion time over t1. And then the second term is plus 0 because we're starting with 0. If we weren't starting with 0, then we would have to factor in whatever we had here. So now we do another inversion. So 3 told us what happened, when we got over here. So that's right before we do. And so let me make sure I got that correct. So we want so now we want to do now we want sorry, our steady state is not quite here. Steady state should really be here. I'll just put it here. Yeah, because we haven't had this slightly different recovery yet. Okay. this is what we want to, this is our bottom line, what we want to figure out, like what is this amount of longitudinal magnetization ready to be converted into transverse that we can record. That's the steady state there. Sorry about that. Okay, so that's number 3. And so then we do an inversion. So we do our inversion, and what's the inversion is just, it's just the negative of whatever we ended up with. So this is just a negative here, mz0, 1 minus e to the minus tr minus ti over t1. Okay, so that's our inversion. So now we're inverted. So we're over here. And now we have to recover for another period of time that's equal to ti. So this distance is ti again. So what is that equation? That will finally give us our final equation. So that is equal to, starting with this equation. So this guy is mz0 plus. That's our initial condition in the differential equation. It's the starting magnetization that we plug into the second term. So that gets substituted into the second term. So this is in second term block. Okay, so so that equation, if we substitute it in, we end up with mz0. So the first term has our 1 minus e to the minus ti, just plain ti, because we're talking about this amount of recovery here, over t1. So that's the first term of the block equation, and then we have to subtract this. It would normally be plus, but we got a negative in front of it, so now we have mz0. Where did I go off? Yeah, okay, there we got plenty of room. So we just insert that one. So here's 1 minus e to the minus tr minus ti over t1. That's all good. And then the part I left out last year, but I won't leave out this year, is that mz0 has to be multiplied by e to the minus t over t1. So that whole thing times e to the minus t, and the minus t is ti. We've substituted in that for ti over t1. Okay, so slightly off. Okay. Still
I
off.
think the second term should be plus, right?
This plus here?
Yeah, is that plus? I can't tell.
No, it's yeah, that minus just came from here. So minus ti over t1. Okay, finally on the board. Okay, so that's our, so that tells us number 5, and then usually we will just algebraically simplify that to get our final solution. So the final solution is the mz equals mz0. Just gather the mz0s together. 1 minus 2 times e to the minus ti over t1 plus e to the minus tr, which came from over t1. Okay, so that's our final, that's the same thing as 5. So that's our final equation for how much longitudinal magnetization we have in the steady state. So this is, m longitudinal in the steady state. We can't record that because that's the very slowly regrowing longitudinal, but we can turn it into transverse and record it. Now, it would be a little more complicated if we turned it into transverse, because if we turned it into transverse, then it would start to get T2 decay. And so then we would have to factor some T2 decay. And when we get to SpinEcho, we'll see that that's what we need to do. But this is our basic equation, and it's a simple illustration of how you use the block equation solutions. And so you use them by, some recovery occurs, you do something that changes your starting point, then you take whatever you got, which already has stuff in it, and you insert it into another copy of the block equation in order to calculate. And you do that repeatedly. So if you have a complicated situation that's not in the steady state, you might be substituting into the block equation solution. You might end up with a giant thing. If you substitute in 100 times, you'd end up with like this giant, effective equation. So this is just a simple idealized one, assuming we have perfect 90, perfect 180. So this is inversion recovery. So this is inversion recovery, no echo. So you might think, well, this sort of looks like SpinEcho, doesn't it? Because SpinEcho is like a 90 and then a 180. But here we did a 180 and then a 90. It turns out you can do inversion recovery SpinEcho, which would be a 180, a 90, and then a 180, and then record some data, and then do another 180, 90, 180. That's what a inversion recovery SpinEcho sequence would look like. Okay, so that's the first one. So this is a very simple one. The first one we didn't have to substitute anything in because we just did one recovery and then we were done. So here, only slightly more complicated. We have basically one recovery, and then we have a 90. So we just throw away that first equation because we don't care. We're starting at 0. And we have a second recovery, which we calculate here, and then we have an inversion. That's here, and then we have a third recovery, which is the one that we're interested in getting. And so this is the end. This is the end result. So this describes what the signal is right at that point. Okay, so that's our basic inversion recovery, and so now what we need to do is move to an actual echo. So now we have to sort of consider, what if we actually have an echo in addition to various kinds of recoveries? Because then we have to factor in the T2, the other solution to the other part of the block equation, the T2 part of the recovery in the block equation. So for this, I'm going to have to draw out more of a pulse sequence, which I haven't explained yet. But it's okay, we just take it on faith that this is what we're doing. So there's some parts of what I'm going to draw out that I'm not going to explain yet. But we'll hopefully just focus on the parts that I am going to explain. So what this is we want a very simple SpinEcho sequence. So this, instead of a 180 and a 90, this is basically a 90 and a 180. So our SpinEcho sequence. And also the other thing is that our distance between the 90 and 180 is going to be much shorter, because remember, the echo takes, T2 decay takes place about over 1/10 of a second, whereas inversion recovery takes place over like a second or 2 seconds. So we're going to draw out our pulse sequence here. So here's the RF stim. And so first we'll do a 90. So here's a 90-degree pulse. Now I'll draw it out like a little sync pulse. We haven't described what a sync pulse is, but we'll talk about that soon. And there's a couple more things going on here. So I'm going to draw out all the gradients. So here's the Z gradient, because there's several of them on at the same time. And here's the, need a little more space than that. So here's the Y gradient, and here's the X gradient. And then last but not least, what the signal we're getting down here. And then underneath, I'm going to draw out the same graph I did before, which was the magnetization longitudinal, because that's mostly what we're going to be recording, what we're going to be making equations for. Okay, so now we have our 180 here. And now this time we're going to wait a long, and this time here is the tau time. So that's the time of that we wait the same amount of time in order to get our echo. So we expect the echo the same amount of time after we did that 180. So what are some of the other things in here? Just taken with a grain of salt. So one of the things we have to do is select a slice. So here's selecting a slice. That's how we do that. We haven't explained how we did that. This is how we select a slice for the 180. We have to do some phase encoding. Haven't explained what that is. So here's some phase encoding here. And then we have to do a readout. And because we've got a SpinEcho, we go to the corner of K-space, which we haven't explained yet. And we do a positive instead of a negative. And then we do, right around here, we do our readout. And that's also positive for reasons that we'll explain later. So that's our, so basically at this point, we want to be in the middle of our readout. Okay, so this is our basic SpinEcho. So what's actually coming out, RF sig, what's actually coming out? Well, there's an FID here, which we ignore, because we did an RF pulse, 90-degree RF pulse that makes transverse magnetization. Then we do a 180. That shouldn't make any transverse magnetization. If it's a perfect 180, there shouldn't be any sort of XY component. And then there'll be an echo over here. And that echo will be sort of lying on this, e to the minus, it's a SpinEcho, so it's e to the minus t over t2, not t2 star curve. So now what we'll do is we'll wait quite a long time. So in order to not give me some space for my equations, I'm going to edit out that time. So this is, say 2 seconds. So quite a long time. So remember, this echo has to take place over about 1/10 of a second or something, so that's a long time. And so then what will happen is, at a later point in time, we'll do another 90. And so then that will define our, there should be a gap in that guy too. That will define our TR. So what is the TE? So the TE will be 2 times tau, right? So this thing here is the TE. That's equal to 2 times that tau time delay. Okay, so here's our TR, so the next time we do a 90, and then we do another 180, and then we get another echo. So there'll be another, tau here, another tau here, and that's when we expect our echo. So this guy will correspond to another FID, and then there should be nothing happening when we do the 180, and then right around here there should be when we get the big echo. Okay, so that's our, and then we have to do another different phase encode here, and we have to do our slice select here, which we haven't explained, and our slice select here, which we haven't explained, and our rephaser here, which we haven't explained, and then our readout here. Okay, so that's our, it should be the same as the other one. So that's our pulse sequence. So what we want to do now is figure out the equation for the height of the echo. So remember, the echo is just T2. So this graph is, this graph is really just T2. Or just, not T2, what I meant was transverse magnetization. So this graph is RF signal, so that's MT. But now we're going to, for the most part, concern ourselves with the longitudinal, because that's the one that we're sort of preparing, and at the last second we turn it into transverse and then record it after accounting for the T2 decay. So most of the action in the equations will be from the dealing with the transverse, the longitudinal recovery, the z-axis recovery. So one of the homework assignments is to figure out the following. So now we're going to I'll put the 0 down about here. So now I'm going to draw out a graph all the way to the end there of the longitudinal magnetization. So we're going to start at the very beginning at MZ0, because we're assuming that we're starting before anything happens. So this guy is MZ0. And then we do a 90. So there's our 90, goes down to 0 transverse magnetization. Then we get our echo. And so what's going to happen? So the first thing that's going to happen is we are going to recover until the 180. So we recover a little bit until the 180. And then the 180 will negativize wherever we are. And then we'll recover, I'm still on the board, good. Recover like that. And so what's going on here? So we're recovering through 0 longitudinal magnetization when the echo comes. So let's think of why that is. So what's going on is we did a 90, so the magnetization is completely transverse. We allowed it to recover a little bit, so it started to sort of get slightly in the direction of the positive z-axis. Then we did a 180, which is going to flip it down to below the z-axis, and then we're going to wait for the recovery, and everything will come back into the phase, like we saw in the original SpinEcho diagram, but we'll also come back to the 0 on the z-axis at the same time. So at the time that the longitudinal magnetization recovers to 0, that will be the time when the transverse magnetization is the biggest. So that's why we're going through 0 at the point where we get the biggest MT signal. So we're going through 0 longitudinal at the time we get the biggest transverse. So now I'm not going to draw this time gap in. I'll just draw the whole thing out. So here's our MZ0 location. So we just slowly recover. So let's say we recover to like about here. So we just slowly recover to about that. This is drawn more at sort of like actual realistic times, because the echo is pretty, is pretty. Okay, there we go. I'm trying a very slow exponential. One last try on that last bit. It's hard to draw a very slow exponential. Okay, that's good. Okay, so now we got to the point where we're going to do another 90. So now you can see, like, if you want to get a when you want to do these very slow pulse sequences, sometimes you have to wait a long time, and there's always all different kinds of tricks to try to get around that. So now the same thing will happen again, so we'll recover a little bit, and then we'll do a 180, and then we'll recover, and then this is where we want to, so this is tau here. And 2 times tau is going to be equal to our echo time. So there's the time of echo. And then this, keeps going on. Okay, so yeah, so let's just draw that over here. So this is tau, time of echo. And then we have, this time from an important amount of time is this time right here, which goes to the next time we do the pulse. So that time, what is that time? That time is going to be equal to TR minus tau, which is TE divided by 2. That number will appear in our equation. So okay, so that's the time. The time between. That's how long it takes for this guy to recover. Yeah, I'm bound and determined to get my exponential regrowth. Okay, so that's TR minus tau, which is TE divided by 2. Okay, so the first equation I'm not going to derive for you. That's part of the homework. So the first equation is basically, what happens here. So what happens here? So this, we'll call that 1. So I'm not going to derive that because it requires a 90 and then some recovery, and then a 180 and then some more recovery that has that in it. And so we'll just write it out. So our starting longitudinal magnetization here is going to be equal to MC 0 times 1 minus 2e to the minus TR minus TE over T1 plus E to the minus TR over T1 end parentheses. Okay, so this is the homework assignment. One of the homework problems. Okay, now one of the ways we can simplify that is, before we simplify it, before we simplify it, we now have to consider T2 decay, because now we're actually going to say that we're recording a signal. So Antonio, I'll be done in about 3 minutes, 4 minutes. You might have to extend. So So what we're going to do is we're going to do this 90 here, but during this whole time we're going to be getting T2 decay because there's an echo here. So now we have to consider the reduction in the T2 signal, not just the growth in the T1 signal that got turned into T2. And so we have to sort of calculate this amount of time, TE amount of time, and add our T2 decay. And so how would we do that? We would basically just multiply by our T2 decay. So that's the second block equation solution. So minus TR minus TE over T1 plus E to the minus TR over T1. And then that whole thing times E to the minus TE now inserted for our time over T2. So this is, we've inserted this T, which is just whatever the amount of time between the starting longitudinal magnetization that we turned into transverse and then started to decay until this point right here, which is the center of the echo. And so one of the things we can do to simplify this is to basically assume that TE is a lot less than TR. And so if we assume that TE is a lot less than TR, sorry, I forgot the divide by 2. Divide by 2. TE divided by 2. Yeah, so that one kind of messes up our equation a little bit. TE divided by 2. And so one of the ways of sort of getting rid of this is just assume that that this guy is TR is really long, and so we can just blow that guy off. And then if we do that, then we can combine it with this one. And so our final equation is the amount of equilibrium magnetization times 1 minus E to the minus TR over T1 by combining those two, and then times E to the minus TE over T2. So this is our final equation that actually tells us what the contrast in a SpinEcho equation, SpinEcho sequence will be. And it's important when you look at this is, so what is this thing? This thing is a tissue property. This is basically the proton density. Because if you remember back to the very first equation in the course, the mz0 just depends on the number of protons. It depends on the B0 field, but we're assuming that's always the same. So basically it just depends on the number of so that's the proton density. This is another tissue property. Tissue property. And then there's another one here. And then we have several things that we can modify. So here's the knobs on the scanner that we can modify. So these are knobs we control. So let's take an example. If we want to make a SpinEcho sequence that gives us T1 contrast, we don't want T2 contrast. So how do we get rid of T2 contrast? We make a short TE. A short TE will make this E to the minus TE over T2 close to 1. A longer TE will drop it off from 1. So if we use a short TE, we don't get much T2 decay. And so then we can sort of concentrate on this. And so we turn this knob down in order to get a T1 weighted scan. What about the TR? For the TR, we don't want the TR to be too long because it'll get rid of our T1 contrast. It'll go all the way back up to MZ0. And so we want a TR that's kind of not too long, like 1 second. So that's how we would use this pulse sequence to get a T1 weighted scan. But what if we want a T2 weighted scan? In that case, we would run a long TR so that we let our magnetization get almost back up to MZ0, so we don't get any T1 contrast, and then we would run a long TE. We want the long TE so that there's time for contrast to build up between the tissues that have different T2s. So this in one equation gives you the whole concept of why you say T1 weighted, because it's always T1, it always contains proton density, and it always contains T1 weighting, and it always contains T2 weighting, but you can just sort of vary how much of each kind you get by setting the scanner knobs. So this is the, just label this is the SpinEcho amplitude equation. So that's our final answer there. So that's where you would use to try to decide how to set the scanner to get different kinds of contrast. Okay, I think I did this one with a better diagram, and I almost got a good exponential recovery. And so Antonio will end the recording now, and then I'll take some questions after you end the recording.